So, okay. So I think everything is set up. So let's get started. So what we're going to see today is modular programming. So what does this mean? So far we've seen a lot of the OCaml features, right? And these OCaml features, I would say, are features to build small OCaml programs, right? And modular programming, in particular, this lecture is about how do you take these principled ways of constructing small programs and use them to construct large programs? How do you build programs that are maintainable at scale, right? And we are going to, in particular, see features that are quite unique to OCaml, right? So module system is something that ML-like languages, in particular standard ML and OCaml, have had for the past 25 years, right? And Java and C++ are slowly adding modules to their language right now. And in particular, C++20, a new standard for C++ was approved a few days ago. And there we have module extensions for C++. So these are concepts that have been around for a long time in OCaml, and slowly these features are being adopted into mainstream languages, right? So hopefully this will give you an idea of what do we mean when we construct programs at scale, right? And in particular, we are going to see three features for constructing programs at scale in OCaml, which are structures, signatures, and functors. So you will see what these things are in OCaml. So let's talk about scale, right? So in assignments 1 and 2, the amount of code that you are asked to write is around 100 lines of code. Right? OCaml itself is around 375,000 lines of code. This includes a lot of OCaml code, but also OCaml itself is written in OCaml, right? So that's the way of writing. That's a way of bootstrapping the compiler by writing it in the same language. But there is also a lot of C code for the OCaml runtime and garbage collector and so on. In particular, if you take more ambitious projects, right? Hubble Space Telescope has 2 million lines of code, and Facebook has 60 million lines of code. Like, this is just an estimate, but I think this number is from few years ago. I suspect this to be at least 5 times larger, if not 10 times larger. So one thing that Facebook was doing is the number of people that Facebook was hiring was growing linearly over time, and the code that they commit was growing exponentially, right? So they were actually writing lots and lots of code. And Google used to be the case that it was 2 billion lines of code, and I assume this is off by like 10x, right? Actually, you should visit this link. It's a beautiful visualization of the scale of the code, right? So it starts from, like, this is in millions of lines of code, right? It starts from the small and keeps growing. So this is 1 million lines of code, right? Bacteria is 1.1 million lines of code. Yeah, Windows NT was 4.5 million lines of code. And if you keep scrolling down, right, this is like a different scale. So yeah, Facebook is 62 million lines of code. I think this was done in 2015. So you can see the scale just keeps increasing, right? So the original version of Unix was 0.01 million lines of code. But if you look at, let's say, Windows XP, that's 40 million lines of code, right? And Mac Debian, right? Something that came in the same tradition as Unix is now 68 million lines of code. So we can believe that the number of lines of code is only going to keep increasing, right? And it's going to grow exponentially. So the point I'm trying to make is this obviously can't be done by one person, right? So you cannot expect to write this much code, let alone even like understand it, right? So even you can't no one person knows everything, right? So, and no, it's just too complex to build such software without a notion of how to put pieces together, right? I want to build small pieces of software in some language, and then I want to take other pieces of software and then put them together, right? So we have not seen such features in OCaml so far. So with the existing features, it's just too complex to do it. So that is why we want this idea of modularity, right? And what is modularity? Modularity comprises of um, it's about making code into individual modules so that they fit like this puzzle pieces, right? Each module is independently defined. Its interfaces are clearly defined, right? And once the interfaces are defined, you can just put together multiple modules together, right? So that's the idea of modularity. And how does it help with programming? So a developer can write a module, right, where the internals of the modules, the complexity of the module is reasoned about locally, right? And the only thing a user of a module reasons about is just the interfaces, right? I only care about the interface here. If I am module 2, I am trying to use module 1, right? I don't care about what is in here. So that's the like intuitive notion of what modularity brings in. Okay, so to dive in, right? So that's the high level view. So what does modularity actually bring in terms of say a language like OCaml, right? So it brings in three features. So the first feature is namespacing. Right? This is standard. You might have seen this in other languages as well. Namespacing just provides a way for the language to name a collection of related features together. For example, you want to say all the list operations are under this module list so that you can do list dot length, list dot head, list dot tail, and so on. Similarly for set and so on. So, um, so this gives you a way of collecting multiple operations under the same name, but also avoids name clashes, right? So both set and list have insert functions, right? And I want to say this insert function, even though the name is the same thing, this insert function for list is different from the insert function for set. How do you do that? Just namespacing, right? You take the insert function and have it under this module list. So list.insert is different from set.insert. So that is namespacing. So this is just a convenience mechanism, right? So you can name multiple things under the same name. The second one is a little bit more important, right? So um, modularity brings in this notion of abstraction. What is abstraction? Abstraction is the idea of hiding the details of the implementation, right? And only clearly defining the interface so that any user of this module knows only depends on the interface, right? The user does not depend on the internals of the implementation. So why is this useful? It avoids the user breaking implicit invariance in the code. If you only depend on the interfaces, then and you don't depend on some internal implementation details, then you can't break invariance. So for example, consider this example, right? So consider using a list as a stack. So we know we have this list data structure in OCaml, where the basic operations that we have are constructing a list, right, by using the cons operator and taking the head and tail out, right? So you can separate out, given a list, if the list is non-empty, you can take the head out and tail out. So this looks very much like a stack, right? You can use cons operator to push and then pattern matching to pop, right? So this is very natural. So this observation is seems very natural. So you can say, okay, I'm going to use a list as a stack, but list also has other operations, right? List can be sorted. You can ask the nth element of a list. You can remove some element that is deep within a list. You can reverse a list and all these sort of operations, which traditionally might not make sense in a stack, right? A stack, when you imagine a stack, it is a FIFO data structure. It's first in, first out. So removing some element that is deep within a stack is not an operation that you would typically associate with a stack. But list provides all of these operations, right? So this is, if you sort of assume FIFO for a list and provide all the FIFO for a stack and expose all the operations that you can do for a list, you might break invariance because the user might apply some operations which have no meaning in stacks, right? And that's the first one, right? And the second benefit of abstraction is today I choose to implement my stack with a list, right? Tomorrow I might choose to implement my stack with a array data structure underneath, right? If the user of the code only depends on the interfaces and not the actual implementation, as long as I preserve the interface, right, I should be able to change the implementation independently without having the user know about this change. So this gives the developer an easy way of improving their code without having to completely reason about all the different ways that a user of this code might depend on the internals of the implementation. The only thing that they can depend on is the interface, right? And that's the second benefit of modularity, which is that you can change the implementation as long as the interface is maintained the same. Right, so we will see more of this in detail as we go through this lecture, but this is just a high-level idea that I'm sort of giving out. And finally, the third one is code reuse, right? We want to avoid re-implementing features that are already present. For example, when you use a list as a FIFO stack, you might imagine having functions such as what is the depth of the stack, right? And what is the stack empty? And we know we have corresponding functions, list.length for the depth of the stack. And we can check whether the stack value itself is nil, in which case we'll have functions for isEmpty. So we can reuse parts of the implementation. So when you have modularity, reuse also becomes easier. So whatever data structures you build using a list, you can always use the internals, right? You don't have to duplicate the code and re-implement everything from scratch. And preserve the fact that you are still using stack as a stack, not as a queue, for example. So there are three features, right? High level at a high level. So the first one is namespacing. The second one is abstraction, and the third one is code reuse. So for each of these features, you can sort of place one OCaml specific feature. For namespacing, OCaml gives you structures. For abstraction, OCaml gives you signatures, right? And for code reuse, we have a collection of features, functors, includes, and sharing constraints. We will see what they are in this lecture. At a high level, structure is like a value. Signature is like a type, right? And functors are like functions. And includes and sharing constraints have no analog in the concepts that we've seen so far. But these are the high-level concepts. So let's dive in. Let's look at structures first. So what is a structure? Structure provides namespacing, right? So it has to provide a way of collecting together a bunch of operations. And that is precisely what a structure is. A structure is a collection of definitions. We've seen what definitions are. Definitions in OCaml are let some variable name equals something, and that's it, right? So that's one definition. A structure can include multiple definitions. Each of the definitions are evaluated in order, and the structure value can be bound to a name. So the syntax for the structure, how do you write a structure? So here is the syntax. So you use the keyword module. So module is a keyword, right? And you give the module a name, equals struct end, right? That's the delimiters. And anything within this struct end is the collection of definitions. You can have the collection of definitions that goes inside the structure. Actually, I tend to use structures and modules interchangeably, which is fine here. I think it's for the purposes of this class, I think interchanging those two terms is fine. Okay, so that's the syntax. Let's look at an example, right? So in order to make the concepts more concrete, it is better to have a look at an actual example. So what we'll do is the same thing that we explained earlier, right? So what we'll try to do is to implement a purely functional stack, right? A purely functional stack data structure using OCaml's built-in list data structure. Okay, so that's what we are going to do. What do I mean by purely functional stack? So in a purely functional stack, the idea is that the update operations, the push and pop operations, do not destructively update the stack, right? They actually return a new version of the stack for every operation. So when you push, you get a new stack which has the additional element on top, and when you pop, you get two things back. When you pop, if the stack is not empty, you get the popped element and the rest of the stack, right? You get the new version of the stack. So that's the idea. So how do we implement it? So we are going to use lists to implement this, right? So we write module, the keyword module, right? And I name the module stack, and I use the keyword struct and end to delimit the definitions that go within the module, right? And I'm going to implement a few operations. So I want to define what empty stack is. Because we are using list, an empty stack is just an empty list. When you say, oh, give me an empty stack, all I'm going to give you is an empty list, right? And push is implemented such that it takes a value, the current stack, because the stack is represented by a list. Pushing simply conses the value onto the stack, right? And this returns a new stack. We are returning a new list, but list is a stack, so it returns a new stack. Pop has to consider whether the stack is empty or not. So if the stack is empty, then we return none. So pop returns an optional value, right? So if the stack is empty, it returns none. If the stack is non-empty, it has a head and a tail, x and an xs. We simply return a pair of x and xs. The idea is that when you get some x xs, it means that the popped element is x and the new stack is xs, right? And the depth of the stack is just the length of the list. Okay, this should be fairly obvious, right? But I'll stop for questions. So any questions on this? Does anyone not understand what's going on here? All we are doing is we are implementing a stack-like data structure, just using the operations of lists that we've previously seen. Okay, no questions. So okay, so let's keep going forward, right? So if you run this module, you get this collection of operations. We'll come back to this. So how does it provide namespacing? So now, because we've defined this module, right, you can access the empty by stack.empty. Right? When you do stack.empty, you get a alpha list, which is an empty list value, right? And this provides namespacing because the only way this name empty, right, this name empty is within the stack module. So when you just type empty here, this is not defined because it sits within the stack module, right? So this is empty is defined only in this stack namespace, so you have to use stack.empty. So this is quite handy, right? So this is what we've done so far with lists as well. So when I write list.length here, I'm accessing the length function that is defined within the list module, right? Similarly, the empty function that is defined within the stack module. Okay, so that is structure, right? Structure provides namespacing. The next concept is signature. As I mentioned before, right? Structures are like values, signatures are like types. So a signature is just a collection of declarations, right? And it's just a collection of types. So just like a structure is a collection of definitions, signature is a collection of declarations. There is no evaluation because you're just defining types here. The only purpose of a signature is to define types for type checking, right? So there is no dynamic semantics for signatures. There is just static semantics. It's just a collection of types. And Just like we bound a structure definition to a name, we can also bind the signature definition to a name. So how do we define a signature? The syntax is this. So the keyword now is module space type, right? When you write module space type, you say that you're defining a signature. This is the signature name. Oops. This is the signature name. And we use the delimiters sig and end, right? If you just compare this to the structure definition, for structure, we use module name struct end, which has a collection of definitions. For signatures, we use module type name and sig end and a collection of declarations within it. Okay, so what is the purpose of a signature? A purpose of a signature is to um, assign a type to a module, right? That is the only purpose. Actually, that is one purpose. We will also find other purposes as we go along. So here is a signature definition for the structure that we had defined earlier. So the structure had empty, push, pop, and depth functions. So we are going to give a type for that structure. So what we are going to do is to say, I'm going to define a signature with module type, and the type of the signature, I just name it as stack type, right? Stack type is the type of the signature. So I have the delimiter sig and end, and all I have within the signature is a collection of declarations, right? A collection of types. In OCaml, the way you define a declaration is you use the val keyword, right? The name of the function that you are assigning a particular type to. Here it is empty, and you assign the type to it. You say colon, whatever the type of that function is. So here we are saying, okay, val empty has type quote list. Val push function has type alpha to alpha list, which means it takes a alpha, it takes the current stack, and then it returns you a new stack, right? And val pop defines the type for pop. You take the current stack and you return an option, right, of a pair of a value. That's the value that you popped and the new stack, right? And if the stack is empty, then you get none here. And depth is give me any stack, and I will return you an integer. That integer is going to represent the depth of the stack. Okay, so so you can run this, and this will just give you the same thing again. So we define the stack type signature. This is just a signature declaration. So the type of this is just the signature. Okay, so yeah, before we move forward, Jupyter, actually the OCaml top level has handy meta commands for displaying modules and module signatures. So it has this meta command called show module, right? Hash show module. This expects some module name, right? If you type that, you get the module signature printed. So show module name stack just prints whatever the functions are available, right? Essentially, it prints the signature of that stack. And similarly, you can also ask to print the module type of some signature, right? Show module type expects a signature here. We know that stack type is a signature. It is just a collection of declarations, and it just prints that collection of declarations. So this is quite handy, right? So you can say, give me all the list functions here. So it prints a large set of list functions. You can also refer to the documentation, but this is handy. Anyway, okay. So that is a handy way to see what you're defining. Okay. Okay. So we've defined this concept of structures here, and we've defined this concept of signatures here. So far, we've kept them separate, right? I've not used them together. I said structures are like values and signatures are like types. And the interesting bit happens when you sort of apply the types to the values, right? And the way you do that is just like we were able to explicitly ascribe types to terms in OCaml, right? Um, what I'm saying is just like I said, let's say L is int list. So just like I did something like this, where I said, I know this is an alpha list, but I'm explicitly restricting it to an int list here. I can do the same thing for modules, right? What I'm doing here is I am defining a module M, right? I'm saying M is a module, right? Whose type, right? Module type is the stack type, and the module definition is I'm just reusing the stack definition that I had used earlier. So instead of explicitly declaring struct something, a set of definitions and end, I'm just saying M is just a module, which is the same module as stack, and its type is stack type. Okay, so this is similar to, okay, so this just prints M is a module type. This is very similar to this one, right? So just like, doing this, right? So I'm defining L to be a value, which happens to be an integer list. And the value itself is just the value that I previously defined. The value is an empty list. And a very similar thing here. So when you do this, what you get is it just says, oh, module M has type stack type. That's all it says, right? Okay, so let's move on. So far, you might wonder, right? What is the whole purpose of the signature? Because um, the structure type has the same type as a signature. It just seems useless to explicitly be able to define signatures, right? So signatures are quite useful. In particular, they allow you to do abstraction. They allow you to hide certain details of the implementation, right? So here is an example. So our stack had lots of functions, right? So in particular, so our stack had say empty, push, pop, and depth. Let's say I just want for whatever reason, right? I want to expose a module which only provides you this empty value. It doesn't provide you anything else. So I want to hide the existence of push, pop, and depth, right? So I don't know why I would be doing this, but I just want to hide. I want to use the same stack, but I just want to expose empty, and I want to hide everything else. So how do you do that? You can do that by explicitly restricting the type of the signature to just empty here. So let's slowly step through this, right? So here we said module M is stack type equals stack, right? I said module M has the type stack type. Here I'm doing the same thing. I'm saying module M, right, has some type here. I'm actually defining the type in place rather than defining it separately with the module type definition and then using it here. You can also directly define the signature here. I'm defining some signature, but I'm saying that the module itself is just the stack that we defined previously. Okay. So what am I doing here? The actual signature says that module M has a type, module type, right? Because I'm enclosing this within sig and end. All of this is the module type, right? So starting from here all the way to here is just the module type. I'm saying module M has a module type where the only value that I expose, the only definition that I expose is the definition of empty, right? And empty has type alpha list. So even though M is the same structure as stack, I've hidden the existence of push, pop, and depth. So I'm sort of making it smaller in a way, right? So if you run this, you get a type for a module M. So the OCaml top level says that you are now defining a module M, right? Whose type, the thing that follows after the colon is the type, whose type is the type that you've defined here, right? Type is sig val empty alpha list, val empty alpha list, end. end. So OCaml tends to print everything on a single line, but that's fine. I think um, this is still unambiguous and you can parse it. So it says that module M is some module which only has a single definition, empty, and that is an alpha list. I'm not saying anything else about the module, even though the module was made from stack, which has other functions. So why is this useful? In a stack, right, we had exposed all the functions. So we can do stack.empty and stack.depth. Stack.empty is just the empty list. Stack.depth is a function that takes a alpha list and returns you the depth. But in M, because we only expose empty, this would type check. This would actually be fine. But this will break, right? Because we are not exposing the fact that M has a depth function. So M is only exposing the namespace M only has empty, right? So when you do this, empty works out, right? This works out, but depth is hidden. So OCaml complains, okay, M dot depth is an unbound value. So what we've done here at a high level is your module may have n number of functions, right? In a practical sense, you might define your red black tree or a data structure with helper functions, right? You don't want to expose all of the helper functions also to the client. Like helper functions are only meant to be used by the module itself, right? For and in order to do that, you will say only expose those set of functions that I expect the client of this code to use. Every other helper function, you will just hide it from the signature using this idea. You'd say, you would specify the signature such that the only things that go in there are the things that you want the user of this module to use. So that's the idea here. Okay, so let's step forward. So there is this, okay, so there's a question. So yes, Srisha, good question. So we can hide it. And that's the concept that I'm going to get to next. Really good questions, because we are exposing the fact that stack is still a list, right? And we don't want to do that. I will show you how to do that in a moment. Okay, so this is just a matter of convenience. So if you have a code which is going to use stack all over the place, you don't want to always do stack dot stack dot stack dot. So you can use open keyword. So open takes a module and then basically opens it, makes all the definitions from the module available. So if I just do stack, this stack value is unbound, right? But if I open the stack and then do empty, now this works out because I know that stack has an empty definition and that is what I'm exposing. Okay, so the can we shadow previous modules? Yeah, you can shadow it. Yeah, that is what I was going to show. You can reuse the same name and that shadows previous definition. For example, I can just define a module list equals struct 10. So this is a module that does not have anything, and I'm using the previous name list here. So any code that follows here cannot use list anymore because I've hidden the value of the list. This is certainly possible. Yeah, yeah, you can. Yeah. So what happens? So the other thing that you have to worry, just following up on that question from Sarthak, is what happens if I open two modules, right? Both of which have the same definition. So I have a module M, which has a definition of X, which is 10. And I have a module N, which has a definition of X, which is 20. And I open M, and then I open N. So both of these opens bring in X into scope, right? This brings an X into scope, which is 10. This brings an X into scope, which is 20. And we follow the standard rules of shadowing. So everything is lexically scoped. So the latest one is the one that is available in scope. So if I run this and I ask for X, X will be 20 because I opened N later. But if I reorder this one, I'll get 10. Because I opened N first and then M, and this brings in 10 into scope. Okay, so that is open. There is this concept of similar to open. There is a related concept, but a thing that is a little bit different called include. Okay, so include is more powerful than open because it is actually more useful. So include allows you to extend the functionality of earlier modules by using all of the code, but also adding additional functionality. Okay, so here is an example. So the stack that we've defined so far had 4 functions, right? It had an empty definition, push, pop, and depth functions, right? Now, what I want to do is to extend the definition of the stack to support isEmpty function. So what is the signature type for the isEmpty function? The type will be, give me a stack, I'll return a Boolean value, which says whether the stack is empty or not. So if the stack is empty, it says true. If the stack is non-empty, it says false, right? But I'm extending the previous definition. I don't want to re-implement, copy-paste all of the code here. But I still want to expose all of the functionality such that the original stack was there. I'm extending this new thing. How do you do that? So the thing that you do here is we define a new module first, right? I'm saying the new module is M, but this could as well be stack, right? Because of shadowing, you are defining a new stack. So that is also fine. I'm making it simpler here. So I'm defining a new module, which is going to be this extended stack, right? So again, I'm using struct and end to collect definitions. And the first thing I do is include everything that was included from stack. So take all the definitions from stack and then include it in this module. And additionally, define this isEmpty function, which takes a stack. If the stack is empty, return true. If the stack is non-empty, return false. Right? Now, if you look at the type of this, you can see that in addition to the stack that you've included here, which brought in these 4 functions, right? We have this isEmpty signature as well. The signature that we have is val isEmpty takes a list, right? And then returns your bool. Okay, so that gives you a way of extending previous functionality. This relates to code reuse, right? We are not writing all of the code again. We are sort of reusing the stack definition. We can extend it this way. So if you have a list module that you want to extend a new stack, yes, you can. If the stack has few hidden definitions using signature, they can be used in the module where no, you can't, because when you, good question. So Ravi has a question where you say, if you have hidden definitions in stack, when I include it, do I bring in the hidden definitions? You cannot, because the only thing that you can assume about the stack is whatever the signature says. If the signature of the stack says that I only have 3 definitions, I can only include those 3 definitions. Anything that is not exposed by the signature is not exposed, because that would break abstraction, right? That would sort of say you can assume details about things that are, say, local to the stack definition. Yeah, you cannot do that, and it is a good reason that we cannot do that. So any of the local helper functions that you've hidden cannot be used. Okay, and in the same way, we included modules. You can also include module signatures. So after opening, can we still access? Yeah, you can. Yeah, you can still do that. So the question is, I've opened the stack. Does that mean that I cannot use stack.empty anymore? No, you can use stack.empty. So open the stack and then stack.empty still works. Empty also works. Okay. 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 So just like we use include for the modules, you can also use it for module types to include module types, extend module types. So here I'm defining a new module type empty, and I'm extending the stack type by including it. I'm adding this isEmpty function additionally, right? So what would this do? This would say, oh, I'm defining a new module type, right? And the things that it has is everything that the stack type has, right? And this additional declaration that I've included, right? So that's the idea here. So include can be used in both the modules to extend other modules, as well as module types to extend other module types. Okay, so we've seen two things, right? We've sort of seen both open and include. So what is the difference between open and include? The way to sort of look at this is open is only meant for ease of local programming, right? And include is actually extending the functionality. How can you see the difference? Let's say I am defining a module M1 where I'm just opening the stack in the body, right? So I'm saying struct open stack, and I'm defining a module M2 which is struct include stack end, right? So we call this informal definition, right? When you open something, you are using it for local convenience, right? You are not extending the module, but when you include something, you are actually extending the module definition that you are describing, right? So in accordance with that informal definition, if you run this, you will see that module M1 is empty, right? So it doesn't have any declarations within it. You cannot use, yeah, module M1 is completely empty. So that it doesn't have anything because we've used open, and the purpose of open is for local ease of programming. You can open something, you can locally use it, but you're not extending the module. But include actually brings in all of the definitions and is exported from the module in which you included the other module, right? So M2 has all the four functions that stack module defines, right? So the purposes are different, right? When you open, you're opening for local use. When you include, you are actually including it with the idea of extending the functionality that is provided by the current module. Oops. So this particular example completely describes what is the difference between open and include. Of course, you can't. I think this is sufficient to know what is necessary to know about open and include. Right? Yeah. Okay. So this is precisely what I mentioned earlier. Okay. So I'll try to sort of hint towards what Srisha was asking earlier, which is we are still revealing the fact that the stack was implemented using lists because of the type that we see. Can that be hidden or abstracted away? Yes, we can. And that is the purpose of abstract types, right? So far, we've seen how to collect definitions under the common name, right? Namespacing, but the implementation details are still visible. So recall that this particular thing is just a reverse apply, right? So just to make sure you understand what's going on. Oops, this is a handy thing. So what is the type of this? It takes a value, it takes a function, applies this function to a value. It's like it takes an x and an f, and it does f of x, right? So that is the whole definition of this. It's handy because you can pipe, you can use this as a pipe operator. So whatever output that you get here, you pipe to the next function, you pipe this to the next function, and so on. This reminds you of Unix pipes, and it's handy that way. I'm using it here. Um, so okay, so what are we doing? That's the syntax. So what are we actually doing here? So I define a stack S such that it starts with an empty stack, and I push 1, push 2, push 3. Right. So if you look at stack S, the stack is 3, 2, 1. As Srisha had observed earlier, right? The even though I've been calling it stack, 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 the type says it is an integer list. Right. So I can apply nonsensical operations on this particular stack, right? In particular, I can use list.sort in order to sort the list. So this is the comparator function, which sort of says what is whether the two values that you are comparing are equal or less than or greater than. And sort expects a function which is an alpha to integer. So if it is negative value, it is less than. If it is equal, if it is 0, then they are equal. If it is greater, then they are. If it is positive value, then it's greater. So I'm just passing minus as a higher order function. Those are just details, right? That doesn't matter. That's sort of not what I'm getting to here. But you can use sort on this stack, right? You get a stack which is 1, 2, 3. Like typically we don't associate a sort function with a stack, right? And this is not what we want the user to do. We don't want the user to do these operations. We want to restrict the user from applying things like list or sort. The problem is that we are exposing the fact that this is an integer list. So we need to hide it. And how do we do that? So we have this idea of abstraction, where we use an abstract type to hide the implementation, right? So here is a definition of an abstract stack type, right? So I'm defining a signature, a module type. That's an abstract stack type. Because I'm defining a signature, I have a delimiter sig and end. And in particular, this is the key point, right? So I'm defining a new type. I'm declaring a new type, alpha t, but I'm not saying what the actual constructors of the type t. I'm not revealing any information about the type other than just saying, oh, it's a t. It's a type t, and it's a parameterized type. It takes a polymorphic variable alpha. That's all I'm saying, right? And I'm not giving any other information about this type. And hence we call this abstract type. So because this is completely abstract, what can you do with these types, right? The only things that you can do with this type are the things that are defined in this set of declarations here. The definition empty gives you a value whose type is alpha t, right? And push takes an alpha t, gives you an alpha t. Pops takes an alpha t, returns you this pair of optional values. Sorry, optional pair of values. Depth gives you this function which takes an alpha t and returns you an integer, and is empty takes an alpha t, the stack, and then returns you a Boolean value. The thing that we've critically done here is we've hidden the fact that this type hides the fact that it doesn't tell you anything about how this is implemented, right? It gives you a contract that is just fully defined in terms of this interface. You cannot use this type to do anything else. You cannot introspect the type. You cannot ask whether the type is, say, integer, or this type can be sorted. None of those are available. The only things that you can do with this type are the functions that are defined here, right? And that gives you the abstraction, right? And this is a standard notation that we use in OCaml. So we sort of say the module type sort of defines what it is, and we always use the type t to define a value of that type. So how do we actually use it in practice? I'll just take a minute or two and then finish it. So I have defined the abstract type here, right? Let me run this. So The signature again says just the same thing, right? It doesn't reveal the details of the implementation of the type. Now I can take my original stack, right? I take my original stack, which is the stack here. I include it in the module definition. I declare a type where internally the type is just alpha list. So within the module, I have to expose the fact that this alpha t, the abstract type, is the concrete type alpha list, right? But I specialize the signature such that it does not reveal the type, right? The signature makes the type abstract. So even though the structure says type alpha t equals alpha list, this information, right, this fact that alpha t is implemented with the alpha list is hidden by the signature, because if you look at the signature does not say anything about what alpha t is. And that's the key bit. So once you do this, right, um, yeah, okay. So I think I need to change the definition somewhere. Yeah, okay. So this should work out. So I've defined the abstract stack, right, which has an abstract stack type. Now I can create an abstract stack which takes an empty, pushes 1, pushes 2, pushes 3, right? At this point, all I know about this abstract type is it is an integer abstract stack. It doesn't print a 3 to 1 now because I don't know that it is a list. I haven't exposed to OCaml that the implementation of this is an integer list. So it just prints abstract, but I can still apply interesting operations on it, right? If I pop this, I should get a 3 out and I should get a stack out, right? That is still usable. So if you pop this, you get a 3 out and you get some stack out. So this is how we build, we add abstractions. So now that you've made the implementation details abstract, you can no longer do sort, because sort is not a thing that is defined on this abstract type. I'll stop here. I think we can continue with the rest of the lecture on Friday. Any questions? I'll wait for a few minutes, and you can ask any questions if you have.
Hi, sir. Following up on my previous question, so the
Yeah.
include thing feels a bit like inheritance. So, is there something equivalent to protected keyword? Because that seems like something. Um,
No, we don't. We don't have anything similar to protected. You have no. Right. Yeah. The observation is correct. Okay. So you have a private one, you have a public one, and then anything that is public is what is included, but you don't have anything that is protected. No. Um, yeah. Any other question? Okay. So yeah, in the rest of the lecture, what we'll see is a little bit more advanced uses of these abstractions and so on, so that we can construct reusable code. But I think after this lecture, I can release you the third assignment, which will be um, the use of side effects and modules. Anyway, so I'll stop here. Thank you very much.